Now, most sulfur plants are based on the Claus process, developed by Carl Freidrich Claus in 1883. He discovered that the H2S reacted with air over a catalyst directly to form sulfur and water. The Claus process is highly exothermic with low efficiencies. Reaction control is difficult, and there's a high risk of overheating the reactor. So, enter the modified-Claus process. This includes a highly exothermic thermal combustion reaction, followed by a moderately exothermic catalyst reactor section. And there's various configurations of this. They're a function of acid-gas feed compositions, minimum recovery efficiency, and maximum throughput. Also, the available utilities will depend on what kind of setup you need. So this is a comparison, kind of basic flow chart between the Claus process and the modified-Claus process. You can see with the original Claus, it's just one vessel. The furnace is actually within the same converter vessel there, but it's just that one thermal reaction going on. And then we see with the modified-Claus process, we have the reaction furnace where the thermal reaction takes place, but then we have at least two more catalytic stages after where the catalytic reaction takes place. And another sort of flow diagram here. We can see our feed streams going into the sulfur recovery unit include the gas sweetening unit, that's the amine unit, and then the sour water stripping unit if we're dealing with refineries. And then most SRUs today now use a tail gas cleanup as well to get the efficiency that much higher, hopefully up into the 99 plus range. And then we have incineration of our sulfur products that are turned into SO2 and vented out the stack. And then of course our product, our liquid sulfur, coming out the rundowns of our condensers, and that's degassed in degassing pits and then cooled and stored. Now we have a graph showing the temperature versus the conversion efficiency for the modified-Claus process. And we can see here that for the highest recovery efficiencies, the Claus reaction is favored with a decreasing temperature. So what is recovery efficiency? It is the amount of H2S that's converted to sulfur vapor and subsequently recovered in the condensers as a liquid. So it's our recovery conversion, or our conversion efficiency, minus our sulfur vapor and any entrained liquid sulfur. Now, a two-converter Claus plant should achieve at least 96% recovery efficiency. And then if you add another converter for a three-stage, we should achieve 98 at least. Now, I'll talk about the main potential losses to recovery efficiency. So we have catalyst deactivation, and that can be thermal, mechanical, or chemical. It can be from soot or fouling. It could be from sulfation, or you could have poisoning from VTEX breaking through into your converter. Also, off-ratio control is a big one. It has to do with the tail gas analyzer and air demand analyzer, which we'll get to. Excessive converter dew point margins. We want to maintain a nice little 10 degrees centigrade margin above the dew point temperature in converters 2, 3, or 4. Converter 1 will run hotter so that we can promote hydrolysis of COS and CS2. Which brings us to the next potential loss. If we have poor hydrolysis, that's a major contributor to losses. Then a poor operation of the demister pad will create sulfur fog, and this is also a big contributor to losses to our efficiency. And we also want to keep that final condenser outlet temperature to about 125 degrees Celsius. And anything higher, and you will notice losses due to vapor carryover. Excessive turndown is also a major one, especially nowadays. We're seeing more of this. The sulfur plant doesn't like to run when the feeds are turned way down or we have poor quality feed streams. It has a hard time running way below design capacity. And then our day-to-day operational upsets, which can really cause any of the above losses to happen. So some configurations, we have straight through, we have the split flow, and then we have other things like sulfur recycle and direct oxidation. And these all depend on the amount of H2S in the feed stream. A split flow process may be preferred over a straight through one if the H2S concentration is less than 50%. And this is where 1/3 of the acid gas is burned in the furnace, and then the other 2/3 will bypass it. So with that split flow design, that 1/3 going through the furnace is actually completely oxidized into SO2. And then that sets us up with the nice 2:1 H2S to SO2 ratio for the first converter. And that's key. So these all depend on, well, these are so we can achieve the proper reaction furnace temperature and then still get our 2:1 ratio. And it's all dependent on the acid gas quality. And these are some flow diagrams of those different variations. So we have the straight through, it's pretty simple, basic, and then we see in the split flow there we have the bypass where 2/3 of it is going and meeting up before the first converter. Then we have our sulfur recycle, which is exactly that. The tail gas, or a portion of the tail gas, keeps getting recycled to try to improve that efficiency. And that would be like a high turn down scenario. And same with direct oxidation. There's not even a furnace. It's just going right to the first reactor. Here's a conventional layout of an SRU, just straight through process here. We have our air and our feed acid gas going in. Then we have our waste heat boiler attached to the back of the RF. Our first condenser, then we have reheating and converting stages, which each follow a condenser. This is a 3-stage plant. And then we have a coalescer at the end, and then it's going to the tail gas treating unit. So this page is some general guidelines for achieving a strong performance from your SRU. So maintaining the correct process chemistry, which is that 2:1 H2S to SO2 ratio, this is perhaps the most critical one. Then we also want good process control. And that includes the upstream units like the amine and the SWS unit. And then directly in the SRU, we need our instrumentation to be calibrated. We need everything to be controlled how we want it. And then we also need to optimize our process parameters. And mainly that includes temperature. We want to make sure our reheaters are all achieving the right temperature for our converter inlets. We want to make sure our condensers are cool enough to condense all the sulfur that we can and minimize vapor carryover. Then lastly, we need a knowledgeable team of operators, maintenance, instrumentation, and management. They're all equally important in this, ensuring the performance of the SRU is good. So we'll talk a little bit more about this H2S to SO2 ratio. We want to ensure that this ratio is achieved at each catalytic stage. And to do this, we have a ratio controller which controls the main combustion airflow based on the acid gas flow rate. So that's our bulk tuning. And then we have some finer tuning where the tail gas analyzer calculates the air demand signal, or ADA. And this regulates the trim airflow to the furnace. Now that finer tuning uses a air demand analyzer, and that formula is for its signal. So it's based off the tail gas analyzer, or the tail gas ratio. So if you look at the formula, if we plug in a perfect ratio of 2:1, that's 2 H2S to 1 SO2, that gives us 0. So the perfect air demand signal is 0.0. Okay, so this page, we have the conversion efficiency versus the air demand signal. So the key takeaway from this graph is that any time the air demand signal goes outside plus or minus 0.5%, there will be an immediate loss in recovery efficiency. And it doesn't take much to get outside that range, so we need really smooth process control, and we hope our feed streams are consistent. Another takeaway is that the recovery loss gets a lot worse when the air demand goes negative. And to achieve a negative air demand, that occurs when the ratio gets too high.